Okay, let's get rolling. So, I find fluid mechanics quite interesting. I don't find fluid flow in pipes all that very interesting, but actually it's probably a staple of one of the things that you perhaps want to know how to do, from natural gas pipelines to flow in well bores. Actually, the same principles apply, as it turns out, to flow in porous media, which are often imagined to be bundles of capillary tubes, very small diameter tubes which represent the pore space of porous media, petroleum reservoirs, aquifers, and we use the same expressions that we'll talk about in this class to be able to understand what's going on. And so what I thought we would do today, just to get things rolling, is to just look at some videos to get us in the mood. I think we're in good shape for where we are. We've looked at this one before. So one of the underlying tenets of
If the pump's not on.
fluid flow has been that we can represent behavior if we satisfy these three requirements of dimensionality. So similitude. So it has to be geometrically similar. So if you do experiments on a pipe and want it to represent a different size pipe, then it has to satisfy the geometric requirements. And basically our geometric requirements are going to be the length of the pipe to the diameter ratio is one characteristic non-dimensional group, and also the relative roughness on the edge of the pipe, which would be, in this case, it would be the roughness on, oh, it doesn't show. I guess I can't point. It would be the relative roughness on the wall, epsilon as we called it last time, divided by the diameter, which characterizes the change from one flow regime to the other. So geometric similitude is important. Kinematic similitude is important because we want things to be flowing at the correct flow regime. And as we cycle through this, all that's happening in this particular example is that the flow starts off to be slow and then it speeds up. And you can see as it starts off slow, you see this little wavering in the dye as all of a sudden it starts flip-flopping. And as the speed picks up, because the flow rate in the pipe is increased, then you get a larger amplitude in this undulation, which is really indicative of eddies forming close to the walls. So we want to be able to run our experiments to the right Reynolds number. And finally, we want to be able to calculate something about the system. And to be able to calculate something about the system, we're interested in knowing something about, for instance, the pressure drop that will occur along the length of it, because it tells us something about the energy we have to put in a pump to be able to pump a given volume of flow along the length of the pipe. So those are the three requirements that we have: geometric, kinematic, and dynamic similitude, which are embodied in ratios of the length dimensions, including the roughness, the Reynolds number for kinematic similitude, and Euler number similarity in terms of the pressures we have to apply upstream to drive flow. And so that's essentially what we would like to look at. If we, I said I can't get very excited about pipe flow, but actually, no, this is not relevant to pipe flow, let's avoid that. But pipe flow is incredibly important for us in many walks of life. We mentioned last time about the supply chain of natural gas around the country, for instance. And I'll shut up for a moment.
Fireball there last night, just around dinner time. Dozens of
This is certainly in your lifetime. It's probably 2 or 3 years ago. I guess we'll find out.
Homes destroyed after a huge explosion last night. It was apparently caused by a broken gas line. It happened in a San Francisco suburb very close to San Francisco International Airport. Priya David Clemens is at the scene in San Bruno this morning with the latest. Priya, good morning.
Erica, good morning to you. We're right at the edge of where the fire stopped. I want you to take a look at this devastation behind me. You're going to see burned out cars, the firefighters still working to make sure all the smoldering flames are out completely. We're seeing little pockets of flames still pop up here and there. See, this home has been completely flattened. This is a scene that has been repeated dozens of times throughout this neighborhood. Parts of San Bruno, California were turned into a raging inferno around dinner time Thursday evening. Flames roared some 60 feet into the air as block after block in this residential neighborhood, about 5 miles from San Francisco's airport, were engulfed. Witnesses reported hearing and feeling a large explosion, leading to early speculation that a plane may have gone down.
It sounded like a jet, almost like just a giant roar, and then the biggest boom I've ever heard in my life.
But it was a high-pressure natural gas line that ruptured, caused the explosion, and then fueled the spectacular blaze. The local utility company, Pacific Gas and Electric, says they will be accountable if it's determined they were at fault.
A terrible, terrible tragedy has fallen on our city this afternoon. Our main concern as public officials here, making sure our citizens are safe.
The view from the sky revealed a large swath of the neighborhood reduced to embers and ash. More than 50 homes were destroyed and more than 100 damaged.
But I lost everything. I understand that. It's gone. It's history.
As firefighters fought the blaze from the ground, airplanes swooped in, dropping flame retardant in a desperate attempt to keep the blaze contained. Images we're accustomed to seeing during fires in the forest, not the suburbs.
We're asking anyone that is evacuated, get onto the bus.
So California seems to get it all, doesn't it? It's not pipelines blowing up, it's droughts. It's not droughts, it's forest fires. If it's not forest fires, it's earthquakes. And I guess this is just a repeat of the explosion, I guess. So with a lot of expletives, I guess, removed. So RT is Russian television, I think. So interesting, just driving off in a car. I guess, does it have a video, audio? It does have audio somewhere. Yeah. I guess he's a little surprised. I guess he, or she, it could be she, a little surprised at what might be going on outside his window. And I guess, of course, the good news is I presume they survived, right? Given that they had a video to share with someone. So anyway, okay, so that's done. And so I say that pipelines don't seem very interesting, but actually they're quite topical in many of the things that are going on right now. And so this is going to
Today, the head of pipeline safety in the U.S. told Congress that 2013 was a banner year, with deaths from accidents at a 5-year low. Construction of one major pipeline is tied up in a debate between jobs and safety. A company called TransCanada wants to build the line from Canada all the way to Texas, and Dean Reynolds looking into this.
The wide open spaces of central Nebraska are an unlikely battlefield, but this is where the two opposing sides come head to head in the fight over the Keystone XL pipeline.
Where it's going to cross.
As now proposed, the pipeline would run right under Jenny Harrington's family farm. We spoke with her a few weeks ago.
Like a new roof, it's pretty great in the first 10 years, but you get 15, 25 years down the road, and pipelines are going to leak, are going to rupture.
And if this one did, opponents say it could have a devastating environmental impact. The pipeline would run about 5 to 8 feet below the Nebraska topsoil, but on top of the Ogallala Aquifer, which provides nearly 2 million people with drinking water across 8 states.
You can't see the Ogallala Aquifer, but it may be the single most valuable natural resource the country has.
Greg Autry is the publisher of the local paper and believes oil and water shouldn't mix.
It's not the pipe. It's what's in the pipe.
The oil from the tar sands in Canada is too thick to flow through pipelines, so it has to be diluted with benzene and other chemicals linked to cancer. TransCanada promises elaborate monitoring and protection systems.
The pipeline will bring more than just oil.
It also claims the project will create 9,000 jobs. Nebraska State Senator Jim Smith is a leading pipeline supporter.
With the affordable, abundant supply of energy, that's going to have an impact on our economy.
And Smith says the financial cost of spill cleanups will be an incentive for TransCanada to build the safest possible pipeline.
You're satisfied with their assurances?
I am. With the 59 reinforced safety measures on this pipeline, it's going to be a safe pipeline.
But with the pipeline still tied up in the courts here and the Obama administration deferring an up or down decision until later this year, The debate will likely simmer all summer. Dean Reynolds, CBS News, York, Nebraska.
So you've probably seen those debates. Actually, that's a reasonably fair, two-sided view of what's going on in the debate, right? So energy independence for North America was often quoted during the last presidential election, certainly by the Romney camp and others. But of course, that energy independence for North America was because of Canadian tar sands oil, more resources than in the Middle East together. But it's a very thick crude. It's bitumen that has to be removed, quite disruptive to remove it. I didn't know actually that they had to dilute it with certain solvents to be able to make it to flow, which is kind of interesting. But this kind of balance between energy independence and energy security, which is related to energy independence, and environmental protection, which is kind of an interesting deal. So I guess pipelines do have some interesting components to it, even after I said pipe flow isn't so stellar. Surprising thing for me is the size of these pipelines. So it's probably a foot and a half in diameter, right? Half a meter in diameter. So very, very large for these. And the network of natural gas pipelines which traverse the country is also quite amazing. We've had our own little deal in State College this past year and a half or so. So there's the plans, of course, to change the steam plant on campus, which burns coal right now. All the coal trucks come in first thing in the morning, and it creates steam. It heats the buildings on campus. The steam, surprisingly, is used for chilling in the summer as well. But the plan is to convert it over to burn natural gas instead of coal, which is about maybe half the carbon per BTU of that order, and not quite half the carbon. And so to do that, you bring in shale gas. Shale gas comes into the town. The original plan was to bring it in from the south side of town through these residential areas on the south side of Beaver Avenue, and the residents complained to that, and they basically blocked it. And so it was rerouted, and so this past summer, all of Curtin Avenue, past the gym, etc., was dug up, and the pipeline came there at an extra cost of, I think, a few $1 million to route it that way rather than bring it in. So interesting, desires for environmental protection on one side, but don't put me out on the other side. You'd think that State College would be a pretty environmentally friendly town, but it's kind of this, even though you might desire natural gas, you don't want it to affect you. I always thought that was kind of an irony. And the other thing here, I guess, is related to all this, not related to, I'm just giving us a bit of relief here. So not completely
On
related.
July 5th, 2013, at about 10:50 p.m., an MMA train carrying petroleum crude oil in 72 Class 111 tank cars arrived at Nantes, Quebec. In keeping with the railway's practice, the locomotive engineer parked the train for the night on a descending grade on the main track. After shutting down 4 of the 5 locomotives, the engineer applied 7 handbrakes. Railway rules require that handbrakes alone must be capable of holding a train, and this must be verified by a test. That night, however, the locomotive air brakes were left on during the test, meaning the train was being held by a combination of handbrakes and air brakes. It also gave the false impression that the handbrakes alone were enough. The engineer then contacted 2 rail traffic controllers, one in Farnham, Quebec, to let him know the train was secure, and the other in Bangor, Maine, to discuss the smoking lead locomotive and the problems it might cause for the next crew. As the smoke was expected to settle, it was agreed to leave the train as it was and deal with it the next morning. Shortly after the engineer left for the night, the Nantes Fire Department responded to a 911 call of a fire on the train. Firefighters extinguished the blaze on the lead locomotive by shutting off the fuel. Then, following railway instructions, they turned off the electrical breakers. After discussing the situation with the rail traffic controller in Farnham and an MMA employee who had been dispatched to the scene, everyone departed. With all the locomotives shut down, the air brake system began to lose pressure, and the brakes gradually became less and less effective. About an hour later, just before 1 a.m., the air pressure dropped to a point where the combination of air brakes and handbrakes could no longer hold the train. The train then began to roll downhill toward Lac Mégantic, 7 miles away. As it moved down the grade, the train picked up speed, reaching a top speed of 65 miles per hour. The train derailed just past the Frontenac Street crossing. Almost all of the derailed tank cars were damaged, many of them from large breaches, and about 6 million liters of crude oil began pouring into the streets. The fire began almost immediately, and the ensuing blaze and explosions left 47 people dead.
So many of you might remember that. So this was the Lake Lac-Mégantic disaster, I guess, in Quebec. And so what's the relevance to this in terms of our discussion? Well, one of the options, instead of using pipelines, of course, is to transport cargo by whale. And so I presume that this is probably Bakken oil, which is very sweet crude, kind of quite volatile crude that happened to be filling this train that ultimately rolled in the dead of night into a town and caught everyone unawares and basically incinerated the town. And this is the results from the inquiry, I guess, from a couple of months ago, but the event was maybe 2 years ago. And so, like life is full of many choices, I guess, that we make in terms of what we choose to do. And so pipelines perhaps are interesting and exciting and perhaps useful for us in terms of the things that we end up doing. Okay. So we digress. So let's get back to talking about flow in pipes. So we've made the case that there are some important expressions that we need to deal with. And so I just want to maybe summarize exactly what the important points are. Basically, everything that we will use, what we'd like to be able to do is we'd like to be able to calculate, for instance, size of pump to be able to pump fluid along a pipeline. And to do that, we need to be able to take care of the energy equation, which is our one-dimensional energy equation, which you'll recall comes from Reynolds' transport theorem for taking account of energy. We always write it between the upstream and the downstream. We're able to put components in there like pumps, which is always on the upstream side. This is up. This is down. And what we've talked about for the last couple of sessions, first in the tail end of dimensional analysis, and last time in our discussions about friction factors, is we'd like to be able to account for these frictional losses. These are the dragging my bag across the table losses that are not reversible. They're expended one way. As you flow water one way, if you flow it back, you don't regain them. You've lost it to heat and sound. And they fall into the categories of minor losses, which we haven't said anything about, but are really due to the fact that we have bends in the system. And what we can do, or what we'll find out, is that we can always represent minor losses as a head loss in the system. All the terms of this are in units of length, so a head loss is in units of length, as equal to some factor, K sub L, multiplied by the velocity inertial term, v squared over 2g. And so you'll see that the v squared over 2g refers to the velocity in the pipe at location number 2, but this v here would be the velocity at some location, let's call it A. So whatever the velocity is in this pipe, this would be the magnitude of loss. And this is because this is in units of length, this term here is also, by definition, in units of length. This term must have no dimensions for it to be dimensionally homogeneous. And this number typically varies between 0 and 1 and is often close to 1. So that's and we can the reason for the summation is that if we have a bunch of these individual losses at these bends in the pipe, then we'd want to sum up all of them to be able to represent the overall loss. The major losses, even though incrementally they're quite small, come from losses due to friction on the walls of the pipe. So the major losses are all of the things that we've been talking about related to the friction losses. We've talked the fact that the velocity profile that comes out of this looks something like this. If we are drawing this as velocity, and this is the diameter of the pipe, and this is the a length dimension across the diameter. And we typically idealize this so that it's not this parabolic distribution, but we make it into an equivalent average velocity. And the reason that this distribution is the way it is that viscosity pins the flow velocity to zero at the wall of the pipe because it's attached to the pipe. You can imagine the water being attached to the edge of the pipe, and therefore it's going at zero velocity. Immediately next door to that, the little lamina of water is sliding over it, and it's resisted by Newton's law of viscosity. So in other words, you'll recall this expression here. And so in other words, if you look at the velocity profile relative to this surface, this is just a consequence of this expression here. It says that our boundary condition pins the velocity at zero velocity here. Right next door to it, it's sliding over it slightly faster. It's controlled by this expression, which we don't need to solve. And as we get further and further away from it, we have the largest velocity in the middle of the pipe because it's furthest away from this static boundary condition. And then once we go past this middle point, then it reduces again on the other side. So this is a consequence of this viscosity in our system. And so we tend to take this distribution and make it into a uniform distribution, and then that would be the distribution that we'd use within this expression that we talked about last time, and that is this here. And it says that the major losses are a function, I'll just write it out, of three components. It's a friction factor, which we'll talk about today. It's a length of the pipe that we travel down. So this would be whatever this length would be. And it's this velocity squared over 2g term. And this also would be, I'm going to call it B to represent the fact that it would be whatever the velocity is in the pipe at that particular location. So typically when we write Bernoulli, we're writing the velocity, at points 1 and 2, upstream and downstream. But importantly, when we talk about the major losses and the minor losses, it makes sense that we're talking about the velocities in those fittings or in that pipe. And so the velocities that we have to use here are not necessarily the velocities, average velocities at the beginning and end points of the flow. And so we have to be aware of that. What else? We've kind of defined most of the terms. What we haven't said is that also there's an extra term here that sometimes is a pre-multiplier on the velocity term, which is alpha. We can take it as equal to 1. Sometimes it's different from that, and it really accounts for whether the velocity really looks like this when alpha is equal to 1. This is the velocity, or whether it looks something different to that. where alpha is not equal to 1. But for all intents and purposes for us, we'll typically ignore that. It's not a big effect compared to other effects. So we have, so the main components that we'll want to deal with are the ones that are outlined here. Minor losses due to bends and fittings, which we'll find out how to deal with. Major losses due to flow within the pipe itself, where this small incremental drag due to viscous forces is integrated over maybe thousands of kilometers, right? If you pump gas up from the Gulf to New York City, then that's probably 2,500 kilometers, 3,000 kilometers. It's probably 1,500 miles, right? And so the length becomes a big number, and the diameter becomes a small number, and so this term ends up being a big number attached to this, even though the friction factor, which we'll talk about, might be quite small. And so those are the main components. The other things are ancillary components. And I suppose the other thing that we might want to be able to look at, I think this is kind of an interesting question to look at, is the amount of power we have to apply to get into this. And so if we want to pump it, then the amount of power we apply, this would be in watts. So joules is a Newton meter, which is work. Rate of doing work is joules per second, which is watts. And so the power you have to supply in a pump to be able to give a given mass flow rate, so this is flow rate, equals average velocity times area. And unit weight would be the density of the fluid. Natural gas probably isn't a gas. The fluid you, at the pressures you pump it at in these pipelines, multiplied by gravity. And so we could calculate that. And so that's the basic expression that we will use. And so to be able to do this, we need to be able to figure out exactly what the other components might be. Okay? So let's take a quick tour through what we might need to know. I think maybe the one good thing about pipe flow is it's quite formulaic. If you know what you do, it's really not very difficult to decipher the questions to be able to understand exactly what we might want to figure out. Okay? So let's zoom through this and just make a few points. We've said many things about pipe flow, but the one thing that also is useful is that we will talk in this class about open channel flows. And so what makes a pipe flow different from an open channel flow is that it completely fills the section of the pipe. And so if it completely fills the section of the pipe, then applying an upstream pressure forces the fluid to go down here, as opposed to in a pipe that's only half filled, if you applied a fluid pressure in the top, it would escape in the least viscous, lowest density component, which would be the gas, and it wouldn't drive flow. And so in pipe flow, the flow is being driven by the pressure gradient. The energy we're applying is pressure. And in open channel flow, all that's driving flow is the fact that it has an inclination and gravity is driving it. And so in each one of those, the driving forces are completely different. And so I suppose you could look at it in terms of the things that we've talked about. The important non-dimensional number for this would be the Euler number, whereas the important non-dimensional number in this would be the Froude number. Let's call it dg, right? Is that right? A velocity divided by gravity times a length. So meters per second squared times meters is meters squared per second squared. Square root of meters squared per second squared is meters per second. So if you divide the velocity by that, it's non-dimensionless. So this is being driven by gravity. And so that's the main difference with what we're dealing with. When we looked at the YouTube video of pipe flow, what we saw was initially at low velocities this nice dye profile, which then began to waver. As we said, we increased the velocity, and we didn't really see it get to this. So when we're talking about the behaviors of these systems, there are two things that are important here. One is that the roughness of this wall is what controls this transition, we'll find, to turbulent flow. So we've called this relative roughness epsilon. and there's a diameter that's attached to this pipe. And so in terms of similitude, the two parameters that define whether the model looks similar to real life is the length to diameter ratio and the roughness. It could be to length ratio, but you could imagine that the roughness would have more of an effect relative to the diameter, and it turns out that that's just the case. So these are the two geometric terms which control behavior. In addition to that, it's controlled by Reynolds number, which is a density, a velocity, a length scale, and a viscosity. So the ratio of inertial to viscous forces. And at Reynolds numbers that are relatively low, you get this nice laminar flow with no turbulent eddies here. As you increase the velocity, you start getting intermittent little eddies forming in this system. And then once you get it fully developed, you end up with this kind of, the average flow velocity through this is still kind of uniform on average. But if you look individually at individual locations, you might have flows actually occurring backwards and then ultimately go forwards twice as fast to be able to make up for the loss of velocity. So it's just like looking at the eddies in a stream or the wake behind a ship, that they have some motion to them. And so this indexing with the relative magnitude of the Reynolds number tells us when it transitions from laminar flow to transitional flow to fully developed flow, fully developed turbulent flow. And so when we characterize the behaviors of these systems, then in addition to using Reynolds numbers to do this, the pressure drops on our system, the head loss that we've talked about, is going to be a function of the velocity squared term, how long the pipe is relative to its diameter, and then this ultimate important parameter here that we're going to spend some time talking about today, this friction factor, and trying to understand that. And so the magnitude of this friction factor is controlled by whether it's flowing in these different regimes. It will be different in the laminar regime than it is in the fully turbulent regime. Okay? I don't really want to talk about this other than to say that if you're starting fluid flow up from a big tank where it's moving by definition at V1 equals 0 because the tank is big, then at this point here presumably also V1 might be equal to 0. But clearly in the pipe V2 is not equal to 0. Right? And so it has to accelerate from this point here to become a fully fledged flow. And so you can work out the magnitude, how long it takes to become fully developed flow in terms of its final regime as a distance from going at 0 velocity in the tank to some fully developed flow in the pipe. And the lengths at which it takes to do that change whether you're looking at laminar flow or turbulent flow. And physically all you're doing is you're accelerating something from 0 velocity here to some finite velocity here, and to do that you have to apply some energy to do it. And so if you look, for instance, at the pressure drop along this pipe, you'd have to spend more energy to be able to get this moving. And we can calculate what those are also as a function of the stress regime. And if, for instance, you looked at the pressure gradient applied along this pipe between getting it from going at 0 velocity here to some velocity here which is not 0 and is the same then along this pipe, you have to apply more energy in the way of, you have larger pressure losses because you're accelerating something. It's not just moving at the same velocity. And so we have to be, maybe we have to be mindful of that. Okay, I'm not going to talk about that. We've talked about these before as well. Okay. So we want to be able to represent behaviors. And so you should very well know this expression. So you must know this. And you do know it. So if you know this expression and its derivatives, I apologize for repeating it, but it's worthwhile repeating because it really is fundamental to what we're doing in this section. Plus sum of major losses and sum of the minor losses. And so there aren't very many important things to know about this other than upstream, other than downstream. And the ancillary relationships are that the pump head is equal to I guess we've used W dot. I'll write it out. Power over mass flow rate times G. This is the same, isn't it, as unit weight times Q. This is more consistent with the other terminology that we've used. It's power over G times mass flow rate. And the magnitudes of these other losses. So the major losses, I guess it's the third time we've maybe written this today. Friction factor, length over diameter, V squared over 2G in the pipe. And head losses minor are some coefficient, which is dimensionless, and again V squared over 2G. And again, the velocities in the fittings. And so that's it. If you know that, you know everything about what we're talking about here. And it just becomes a recipe. And so you certainly know Bernoulli's equation. All the units are in units of length. And I guess the other thing is the pump head is positive if a pump, and it's negative if a turbine. So if you're taking energy out of the system, then it becomes negative. So there's a sign convention that applies. And that's it. And so really all we need to understand is a little bit about the component behaviors that we have to understand to represent this friction factor. We know that flows scale with Reynolds number. And for our purposes, Reynolds number will be an average velocity, a density of the fluid, and a characteristic length. Our characteristic length is always the diameter, not radius, and divided by viscosity. And I guess we can imagine that we have laminar flow if Reynolds number is less than 2000, and turbulent flow if Reynolds number is greater than 2000. As a rough idea. There's a transitional flow, but that's not a bad number to remember. And so I'd say that the stuff that we have on that page there is everything that we need to be able to do things for the next little while. So in this, the two important parameters that govern our behaviors are this friction factor, which we like to know about, and also this loss factor, which is similar. You see that they both act on this V squared over 2G term. The only difference with the friction factor in a pipe is it scales, it's per incremental length of pipe, and so you have to multiply it by this incremental length to be able to scale it up to your full pipeline from New Orleans to New York City. This is done per fitting. And so you have one bend, you add one magnitude. If you have 10 bends, then you have 10 magnitudes of this to add. So that's the deal. Okay. So as I say, it becomes formulaic. And so this is just a chart that suggests, if we go back to this, I'm not trying to give you, that this friction factor is a function of two things. It's a function of Reynolds number, and it's a function of relative roughness. And that should make sense to us, right? Reynolds number, because we saw it in the video of the pipe, a nice straight die, increase the velocity, get a little wiggle in it, and then much higher velocity, you get this fully developed turbulent flow. So you could imagine that the resistance on the walls of the pipe might be different as you go from these different regimes. And it's proportional to the relative roughness, because it's the relative roughness which is one of the factors that at any given Reynolds number, it triggers this transition from one regime to another. And so we've used this analog before. The reason for golf balls being dimpled is that it makes a turbulent boundary layer, which actually makes the golf ball more efficient in going through the air in terms of less drag, and triggering that turbulent flow by the dimples is what gives it that behavior. And so the relative roughness, we can see, is a property that we'd like to figure out. And this is just a table from your book that basically looks at the magnitudes of absolute roughness of different kinds of pipes, whether it's a wood pipe or a concrete pipe or a cast iron pipe or a galvanized pipe. Does it have plastic or glass? Plastic or glass, you'd imagine, the smoothest. So the roughness in feet or millimeters is 0. Riveted steel would be among the roughest because you have big rivets on the inside of your pipeline. And so if you know what the magnitude of this is, then you can get the magnitude of this ratio epsilon over d. So this is what we'd call relative roughness. And of course this is just a representation of this. Put in your pipe diameter for a given type of pipe. If you know that you're using 2-inch pipe, we'll use metric, of course. If you're using 0.2 meter commercial steel pipe, then automatically you have the relative roughness. You can do the division just as easy, but that's all it is. So we don't particularly need that. We can just do the division. The more important component is that we'd like to be able to figure out exactly what this friction factor is as a function of relative roughness and including this Reynolds number and relative roughness. And so for that, we'll use the Moody charts. And so the important features of this are, if we look at it, is that we said something about laminar behavior. So what did we say? We said 2000. So this is 2000 right here, in terms of our Reynolds number. So it has to be the appropriate density and viscosity have to be for the fluid, the average velocity, but we could do it relative to radius or we could do it relative to diameter. So these are relative to diameter. So at around a Reynolds number of 2000, the initial behavior for laminar flow, at least for a circular pipe, is this term here, which is just the friction factor is equal to 64 over Reynolds number. And so, unfortunately, I suppose, if we look at the head loss for that circumstance, it would be the friction factor times length over diameter times velocity squared over 2g. And I say unfortunately because obviously the velocity turns up in this term as well. And so it's not really defined uniquely unless you know what the velocity is here. If you know what this velocity is, you'd know what the velocity is in Reynolds number, and you'd be able to solve uniquely for this magnitude. If you're looking at the flow along the pipe where you're defining it in terms of a pressure drop, and you're trying to solve for the velocity, then this isn't quite so easy to solve. So in the laminar regime, this is the magnitude of our head loss. This is the magnitude of the friction factor, which goes here. This is, by the way, for circular pipe. We'll find out that for non-circular pipes, we can represent the friction factor as some constant divided by 64. It should still scale, but it's not, yes, some constant over Reynolds number that isn't 64, but will be maybe close to it, maybe not. As we get higher velocities, all of a sudden, as you say here, the transition, so this is a transitional regime. I'm writing over this. So I lied a little bit about this immediate 2000. So it's not quite as simple as that. It's kind of 2000. This is definitely laminar in this region. This is a transition. And then this dashed line here is to wholly turbulent flow. And that's useful to know because the features of this are that now all of a sudden you see that the friction factor is constant for any of these flow magnitudes. It doesn't matter if it's going at 1 meter a second, 10 meters a second, 100 meters a second. The value of this friction factor, which would be the ordinate on this left-hand side, which would be about 0.07, for this particular roughness, would be the same. So that makes it somewhat easier to solve for conditions. We'd like to have fully turbulent flow because it defines our friction factor uniquely as a function of the relative roughness and nothing else, as long as we know that we're going faster than a certain velocity. And so friction factor varies with the flow rate in the laminar regime. It varies with the flow rate in the transitional regime, but it doesn't vary with the flow rate in the fully turbulent regime. I suppose the other important location along here is that these show that this is a rough pipe, and this is a smooth pipe. So you notice that the transition to turbulent flow for a rough pipe occurs at a lower Reynolds number than it does for a very smooth pipe, which would be at a much higher Reynolds number. And so that's related to this triggering, if you like. So the roughness, in some respects, triggers turbulent flow. It triggers it not in terms of time, but it triggers it in terms of the Reynolds number. So as you're increasing the Reynolds number, you'll go fully turbulent at a much lower Reynolds number if it's a really rough pipe than you will do at a very smooth pipe. And so that's useful now. The other important curve on this, certainly in terms of our solution stuff, is this fully smooth curve. So this is the value for, I guess, epsilon over d is equal to 0. And that is, if you had a fully smooth pipe, it's this trajectory along here. So this is epsilon over d equals 0. And that's another useful ordinate, which I guess says the same thing. Actually, no, it doesn't say the same thing as this. It's slightly different. So in this particular case, the magnitude of the friction factor is changing all the time for this smooth pipe. And I guess the argument would be, if it's truly infinitely smooth, if that's a real term, if it has zero roughness, then it tries never to be able to set off turbulent flow because the flow regime is stable all the time. So what sets off turbulent flow is this little undulation on the bottom. It's a bit like the idea of the Tacoma Narrows Bridge. You have flow going across the top of the bridge. You have these vortices being shed off periodically from the top and the bottom. What sets those off is that this structure has some kind of roughness. If it was beautifully smooth flow around the bridge deck, then it would stay laminar all the time. And so in this particular case, the analog for that would be that, in this case, this behavior here for fully smooth pipe, infinitely smooth pipe, never actually does become turbulent because you don't have these undulations to be able to kick off that turbulent flow as a instability basically developing. And so that's kind of what we'll use for the next little time. So we'll use the Moody chart. The Colebrook formula is just a way of being able to define the Moody chart in the non-laminar range. So outside this, it doesn't give you this value, but it gives you everything else. So the Colebrook-White formula basically gives you everything here if you want to be able to use it, but you can just use the charts. It includes the effect of this relative roughness, it includes the effect of Reynolds number, and it's not very easy to use because it has the friction factor on both sides. But this Colebrook-White formula is just a representation of the graph above it, with the caveat that it doesn't represent laminar flow, but laminar flow is always given by this behavior. And so what we'll do is we'll try using that next time to be able to solve some problems where we actually look at pipe flow and try and solve for the things that we'd like to know. We'd like to know what pressure we'd have to apply upstream or downstream, what pumping rates we'd have to, or pumping energy we'd have to apply to move gas from some location to another. I think an interesting question to ask would be, how much energy do you have to expend, for instance, per unit, thermal unit of gas that you bring up from the Gulf versus how much thermal energy you get from burning it. And so you can play around with pipe sizes to be able to look at the relative efficiency of pipes. And presumably, just intuitively, you think that as you make a larger diameter pipe, it should be more efficient to be able to allow larger mass rates of flow, although the capital cost of that pipe would be relatively larger. And so you could do a little balance on those things. So I'm going to leave it at that for now. Okay, thank you very much.